Yeah. Good evening, guys. Are you able to hear me? Am I audible?
Yes, sir.
So listen. So yesterday we discussed about certain points, right? About the about the different kinds of properties of a magnetic material, right? So based on that, today what we'll do is we'll see a video where there'll be a small demonstration shown for the paramagnetic diamagnetic substances. So are you able to see my screen? Yeah. Yes or no? Guys, are you able to see the screen or not?
Yes, sir.
So see. So listen. What will happen is he has different kinds of materials that are present. He has water, bismuth, and aluminum, graphite, all these materials that are present. And when he tries to take a permanent magnet closer to these substances, look at the way they are going to react. Okay. So did you observe what happened to it? So when the permanent magnet is taken closer to water, observe what is happening is the water starts getting repelled. Okay, similarly, you have graphite, aluminum, and glass. Okay, look at the way these materials are going to respond. So you have a nail here, right? So what do you think will happen when this nail is connected to a permanent magnet? So from the concept that we discussed yesterday, what do you think is going to happen to the nail, the bigger nail that is there, when you connect it to a magnet? What is going to happen to it? Let's at least guess. I repeat the question. If that nail is taken and connected to a permanent magnet, what do you think will happen to that nail?
It gains magnetic properties.
So it should acquire magnetism, right? Let's check. So if you observe, the iron nail initially does not have any magnetism. If you observe these pins that are there, right, they are not getting attracted to the steel rod, to the nail, right? But when you connect this magnetic substance, when you connect the magnet to it, then what you can observe is, see, it is able to have the magnetism, right? It is also exhibiting magnetism because what happens is inside the nail, there will be field lines that will be created. So the magnet which is there outside is creating a magnetic field around it. Now this nail is in contact with it. So there is a magnetic field generated within that material as well. And the nails are getting attracted. Okay. Now the next important question is, what will happen to the bigger nail when it is removed from the magnetic material? When it is detached from the magnetic material, what do you think is going to happen? When you detach it from the magnetic material, what do you think is going to happen? Guys, a last warning. If you're not going to speak, I'll just wind up the session. I've already taken class for 2 hours. Okay.
The nail retains its magnetic.
Then what is there, Sanjeevan? Why did it take so much time for you to talk? You want me to ask each question thrice? The energy is getting wasted. I would rather conserve it for a better purpose. No. Why am I even taking this class? And what about others? Others are sleeping. Huh? So see, what is happening is that steel nail, the iron nail is able to retain the magnetism. And this property is exhibited only by a ferromagnetic substance because you can retain it for a longer duration. This is what we call it as retentivity. Okay. Now, next we will see about paramagnetism. So what is basically paramagnetism is? Paramagnetism and ferromagnetism are similar to each other, except the fact that paramagnetism is going to be a weaker magnetism and ferromagnetism will be a stronger magnetism. Okay. So if you see, look at the way aluminum is going to respond to the magnetic substance. So it is getting attracted. So it is called, so aluminum is a paramagnetic substance. Similarly, this is called as liquid oxygen. So what happens to liquid oxygen when you try to pass the magnetism to it? Observe. So you to observe, it is getting attracted. It is getting stuck. So similarly, you take gadolinium oxide. So the cupric sulfate is also a paramagnetic substance. So here, an important property that you need to observe is paramagnetic and ferromagnetic, as I mentioned. Paramagnetic and diamagnetic. Okay, we are going to see the difference between them. In the first case, when you saw water, right, water was repelling the magnetism, whereas aluminum, then you had the copper sulfate, all these materials attract, right? They were getting attracted due to the magnetism. So the materials which are getting attracted are called as paramagnetic substances. The materials which are repelling are called as diamagnetic substances. Why is this happening? Has something to do with the atomic structure of that particular element. Okay. So if you see graphite, look at the way it is going to respond to magnets. It's called pyrolytic graphite. PYROLYTIC. Pyrolytic graphite. So these are superconductors. So this is called as magnetic levitation. Okay, the magnets start levitating. Okay, in the sense it starts flowing in the upward direction.
Most famous and powerful diamagnetic is bismuth, element number 83 on
So bismuth is also a diamagnetic substance. Look at the way it responds.
the bismuth powered boat sails through the bigger magnetic fields. I'm going to check whether or not it is diamagnetic or paramagnetic.
So here is where I want to explain one important point. If you take an object, right, and when you freely suspend it, okay, when you freely suspend it between a north and a south pole, depending on the way this material is getting, the material is aligning itself, the materials can be classified as paramagnetic or diamagnetic. Okay. So, for example, if the material is getting aligned in the direction of magnetic field, it is called as a paramagnetic substance because it is supporting the magnetism. Whereas if the same material is getting aligned perpendicular to the direction of magnetic field, you call it as a diamagnetic substance because it is trying to repel the magnetism. Okay.
Magnetic objects like glass.
So you see glass is suspended, right? When you take the magnetic field and keep it, right, look at the way the glass will turn. But if you see aluminum, right? So observe, it is aligning itself in the direction of magnetic field. So aluminum is a paramagnetic substance. It is not ferromagnetic. Ferro refers only to iron materials. So aluminum is a paramagnetic substance which supports magnetism, means it allows magnetism to pass through it. Or magnetism can be induced in it, whereas a diamagnetic substance will repel magnetic field. Okay, so glass is an example of diamagnetic substance and aluminum is an example of paramagnetic substance. So if you look at aluminum, right, it has an atomic number of 13. So can you tell me the number of the electrons split up in each shell? I'm asking you a question. Can you tell me how that 13 is getting split up? How many electrons are getting split for each shell?
So 2, 8, and 3.
Yes, 2, 8, and 3. So in the last orbit 3, right, what do you have? you have something called as paired electrons and unpaired electrons. So out of the 3 electrons that you have, 2 will be paired and 1 will be unpaired. Correct? Yeah, is it right? And it is because of that unpaired electron only paramagnetism is exhibited by materials like aluminum. So if you see, the main reason for any material to have paramagnetism is the unpaired electron that is present. Okay?
Yes, sir.
Let's take to understand what it means to paramagnetic field dynamics. You have to know what the electrons are. So, for example, blue. See from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p.
Correct?
Now it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become a magnet. And it's that unpaired electron that is freely magnetized and attracted by the magnet. But what about a diamagnet like water?
So when you look at water, right, water is a diamagnetic substance because it was repelling the magnetic field. If you observe, it has 2 lone pair of electrons. When I say lone pair, they both are also paired again. Means if you take water, right, independently you do not have any unpaired electrons, as a result of which it is exhibiting diamagnetism. Means in diamagnetic materials, you will never find electrons which are unpaired. All the electrons will be paired.
It has all its electrons paired. It will not be magnetic. In fact, water is repelled by the magnetic field. The electrons come to low energy because they are moved away from the magnet. In conclusion, it's a paramagnet or a diamagnet. It's supposed to its electrons. In case of a paramagnet, it has at least 1 unpaired electron. In case of a diamagnet, it has mostly paired.
Is that clear?
Yes, sir.
So based on this, what we are going to do is we are going to discuss about how the paramagnetic, diamagnetic, and ferromagnetic substances are classified. One minute. Yes. Now, based on the experiment that we observed, right, we'll see how the elements are classified. So we'll see the comparative study of dia, para, and ferromagnetic substances. So first is the first property. First try to answer them, okay? So just now you saw an experiment. If you take a diamagnetic substance, okay, listen. So when I take a diamagnetic substance, what will happen? What will be the effect of magnets on a diamagnetic substance? Do they repel or do they get attracted? So they repel. Diamagnetic substance repel, and it is a feeble repulsion. Okay. Similarly, when you talk about a paramagnetic substance, there is a feeble attraction. Whereas when you take ferromagnetic substances, what happens is they have a strong attraction. Okay. Next is in external magnetic field. So in external magnetic field, what will happen to a diamagnetic substance is it will acquire, diamagnetic materials will acquire magnetism. Okay, they will get feeble magnetization. But what will happen is they will get the magnetization in the direction opposite to the external magnetic field. Whereas paramagnetic substance and ferromagnetic substance will acquire magnetization in the direction of magnetizing field itself. Okay. Whereas in the case of in the case of paramagnetic, it is feeble. Whereas in the case of ferromagnetic, it will be a strong magnetization. Similarly, when you talk about a non-uniform magnetic field, okay. So when you talk about a non-uniform magnetic field, diamagnetic substances start moving slowly from stronger magnetic field to weaker magnetic field. If you recollect how glass responded, right? Glass started turning in the direction perpendicular to the surface, perpendicular to the magnetic field, right? So they tend to move slowly. It is not a fast motion. If you observe that the glass started moving slowly, right? From stronger to weaker magnetic parts of the field, whereas the paramagnetic substance will tend to move slowly from where? From a weaker to a stronger part of the magnetic field, whereas ferromagnetic will also move from weaker to stronger, but this will be a quick process. Okay. Similarly, if you place a diamagnetic substance in the presence of uniform magnetic field, then what will happen is a freely suspended diamagnetic rod will start aligning itself in the direction perpendicular to the field because it will start moving from stronger to weaker fields. Whereas when you talk about a paramagnetic substance, it aligns itself parallel to the field, but it is going to happen slowly. Similarly, for ferromagnetic substance also, it aligns itself parallel to the field. Okay. The next is susceptibility. So when I talk about the susceptibility value, okay. So susceptibility means yesterday I discussed the extent to which a material can get magnetized. So susceptibility for a diamagnetic substance is small or it is negative. The meaning of negative here means that it can never be magnetized because it will always repel magnetic field. No, you cannot magnetize that material. Whereas when you talk about the susceptibility of a paramagnetic substance, it will be a small number ranging between 0 to some number epsilon, which is a very small value. Whereas when you talk about a ferromagnetic substance, susceptibility is greater than 1000. Okay. This is a very, very, very important point. So how they will ask an exam is, susceptibility of a material in the presence of external magnetic field is negative. What kind of a material is it? So answer will be, it's a diamagnetic substance. Okay. Susceptibility of a material is a small number. What kind of a material is it? Paramagnetic. If it is greater than 1000, it's a very, very high value. You call it as ferromagnetic. Similarly, you talk about relative permeability. If the relative permeability is slightly less than 1, then it is a diamagnetic material. If the relative permeability is slightly greater than 1, then it is a paramagnetic substance. Whereas if the relative permeability is greater than 1000, then you call that as a ferromagnetic substance. Okay. Seventh one. If permeability value is less than the permeability of free space, then if mu is less than mu naught, it is diamagnetic. If mu is greater than mu naught, it is paramagnetic. If mu is very much greater than mu naught, then it is going to be ferromagnetic. Okay. The next important point is effect of temperature. Means if a diamagnetic material has got magnetized, or let's say you're trying to magnetize the material, then the susceptibility of a diamagnetic material is completely independent of temperature. Whether you keep raising the temperature of that material and start magnetizing, or you do it at a normal temperature, it doesn't have any effect at all. Whereas with respect to paramagnetic material, we can say susceptibility varies inversely with temperature. Okay. It varies inversely with temperature. Similarly, if you look for a ferromagnetic substance, susceptibility is inversely proportional to 1 by T minus Tc, where Tc is called as Curie's temperature. So Curie's temperature is generally the temperature at which a ferromagnetic substance will lose its magnetism. Okay. Sarvesh, are you able to understand?
Yes, sir.
Sanjeevan?
Yes, sir.
Nithilan?
Yes, sir.
Ritika? Ritika, are you able to understand? Okay. So removal of magnetizing field. Okay. So when you remove the magnetizing field from a material, then what is going to happen to the magnetization of a diamagnetic material? So magnetization of a diamagnetic material will exist only till the time there is an external magnetic field. Okay. So magnetization will last only till the external magnetic field is applied on it. Okay.
Okay.
Similarly, you talk about a paramagnetic substance that will also lose magnetization as soon as you remove the magnet, external magnet. Whereas when you talk about a ferromagnetic substance, it is going to have magnetism existing for a longer duration. And this property is what is called as retentivity. This is called as retentivity. Okay. Next is variation of M and H, where M is called as magnetization and H is called as magnetizing field intensity. Magnetizing field intensity. Okay. So what will happen is M changes linearly with H, in the sense if M is taken here and H is taken here, M changes linearly with H. Now, here what will happen is, in a case of a paramagnetic substance, M will change linearly with H and will attain a saturation point at a very low temperature. Okay, at a low temperature and very strong magnetic field. Whereas in the case of a ferromagnetic substance, M and H will vary like this.
Yes.
Okay. Next, there is something called as hysteresis effect. So hysteresis அப்படின்னா lagging. Hysteresis means lagging. So when you talk about hysteresis, observe the magnetic induction vector generally doesn't show any hysteresis for a diamagnetic substance, whereas for a paramagnetic and diamagnetic substance, there is going to be no lag between the magnetic induction and H. About this hysteresis, I'll deal in detail. Okay, that is a separate topic. Whereas ferromagnetic substances show hysteresis. And the last property of all is physical state of the material. So when you talk about a diamagnetic substance, it can either be a solid, liquid, or gas. And when you talk about a paramagnetic substance, it can be a solid, liquid, or gas. And when you talk about a ferromagnetic substance, it is normally solids only. So ferromagnetic substance, because we talk about iron, they are normally solids only. And the last part is examples of ferromagnetic substances are bismuth, copper, lead, silicon, nitrogen at standard temperature and pressure. Water and sodium chloride can also be considered as diamagnetic substances. Whereas when you talk about paramagnetic, aluminum, sodium, calcium, oxygen, and you talk about CuCl2. These are all paramagnetic. And you talk about iron, cobalt, nickel, all these things, Fe2O3 and all nickel means aluminum, nickel, cobalt, alloy. So if you talk about all these materials, they are all ferromagnetic in nature. Okay. Now, having said this, I'm going to discuss an important topic which is called as hysteresis. Okay. So if you recollect the concept from yesterday, we saw mu is equal to B divided by H. So which implies B will be equal to, mu into H. So from this, I am able to observe that B is going to be directly proportional to H. Okay. So if I say B is directly proportional to H, then I try to plot a graph between B and H. What am I supposed to get? I'm supposed to get a straight line like this. But to our surprise, what will happen is you will not get a straight line at all. Rather, you will get a curve. That curve has a name, concentrate. Okay. So I want everybody to draw this graph. This B stands for magnetic induction and H stands for magnetic intensity. Okay. Now what will happen is, initially, let's say I am starting at 0. Means the magnetic substance is not exposed to the magnetic field at all. Now, as you keep increasing the value of H, what can happen is the value of magnetic field getting induced will also increase, but it will not increase linearly. Rather, it will go in a curved path like this. In the sense, what I'm trying to say is, even for smaller value of input, you can see a greater value of output. So what I'm trying to say is, even smaller input can generate greater output. Okay. After that, even if you keep increasing the value of H, means even if you keep increasing the value of input field intensity, you can observe that it attains a maximum value that is called as the saturation value at a particular point. Means beyond which, how much ever you try to increase the value of H, the value of magnetic induction will not increase. Is it clear till this point?
Yes, sir.
Okay. Now I have a question. Now when you remove H, when H is removed, okay, then what should happen to the material? H is removed means when the input magnetic field is removed, what do you think will happen to the acquired magnetism of the material? What do you think will happen to the acquired magnetism of the material? Will it tend to become 0 or will it still be the same?
Tend to become 0.
It will tend to become 0, right? So if at all I say, see, I'm drawing the graph again, concentrate, okay? There's a tricky part. If this is H and this is B, as you keep applying the field, the value of B will increase in this way. And it will reach a maximum value at this point, right? So when the value of H is removed, right, what we expect is the curve to come back to zero in this path only, right? Is that what we expect? Means you will expect that the magnetic field will become zero by coming back in the same path. Is it right? That is what we expect. But to our surprise, what will happen is it will not retrace the same path. Rather, it will start bending in this way. Means it will follow some other path so that when H is zero, there will be some amount of B which is not equal to zero. And this value is what is called as retentivity. So what is retentivity? It is a property of a ferromagnetic substance to retain magnetism even when the magnetizing field is removed. I repeat, it is the property, it is the value of magnetic field held by a ferromagnetic substance even when the magnetizing field is removed. After this, what we can do is, when you start applying the value of H in the reverse direction, means when you start, see, suppose initially this was North Pole, this was South Pole. In the presence of it, let's say you kept a magnetic substance like this. Now what you're doing is you're reversing the direction of magnetizing field. When you reverse the direction of magnetizing field, what will happen is the magnetic induction direction will also change. And at a particular point, you can observe that the magnetic induction becomes zero. Right? So what is happening here? This is the value of H for which the magnetic induction becomes zero. So after that, if you keep increasing the value, right, it keeps still increasing its value and it will start attaining B max in the negative direction. Right? Again, what you'll do is you'll remove the magnetic field. You'll remove H. Then what you can observe is that it follow a path like this. Now this time, this will become the retentivity. After this, if you start increasing the value of H in this direction, then it follows a loop in this way, which is called as hysteresis loop. Okay, this is what is called as hysteresis loop. And why is it called as hysteresis loop is because there is a lagging that is existing between the value of B and H. Okay, so this is what happens. Are you guys able to understand?
Yes, sir.
Okay, this loop is what is called as hysteresis loop. So here, based on which we need to see two names, which is called as retentivity and this is called as coercivity. Okay, so first we will see what is coercivity. So please write it down. Coercivity is the intensity of the applied magnetic field. It is the intensity of the applied magnetic field required to reduce the magnetization of the given material to zero. So it is the intensity of applied magnetic field required to make the magnetization of a given material to zero. Similarly, what is retentivity? So retentivity, as the name suggests, it is the capacity of an object to retain magnetism after the external magnetic field is removed. Okay. So this is all about the hysteresis loop, and this is a very, very important point. So based on this, what we can summarize is, if you talk about hard iron and soft iron, right? So hard iron will have generally, that is like steel, it will have more retentivity and coercivity. Whereas when you talk about soft iron, it will have low retentivity and low coercivity. Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
So this is all about the properties of magnetic substances. Okay, the last concept that is left out is Earth's magnetism. Okay, so Earth's magnetism is a concept which I'll explain tomorrow, and with that, this chapter is over. So, any other doubt from today's class?
No.
Okay.
No, sir.
So I suggest everyone to go through these concepts because it will be confusing in the first part. In this chapter, the toughest part is theory only. If you're not good with the theory, you will not be able to attend the questions. So I suggest you all to go through the theory again. Okay.
Okay, sir.
Apart from that, Earth's magnetism is a very, very simple concept. Don't worry about it. That I can explain it tomorrow. And tomorrow, maximum 40-45 minutes, we'll be done with this chapter. Okay.
Okay.
Yeah, that's it.
Sir, Celsius temperature, I know.
Curse is Curie's temperature.
Curious.
Curie's temperature apdina, it is the temperature at which a ferromagnetic substance will lose its magnetism.
Okay, sir.
Okay. Yeah.
Thank you, sir.
Yeah.
Thank you, sir.
Okay.